Hello, my name is Kaiwa Dashobe Makezi, and this is a presentation about machine learning. So to start us off, we're going to define what machine learning is, and machine learning is just a field of study that gives computers the ability to learn without being explicitly programmed. The two types of machine learning, one of them is supervised machine learning, and the other is unsupervised machine learning. So about supervised machine learning, this is just used for data that is already classified, data that has features from which information can be deduced. And this diagram is illustrative of that. We have two sets of data points. We have data points that are labeled as red and those that are labeled as blue data points. And for this case, we are taking this as a weather forecast, and the red is representing, let's say, the days that did not have rain, and the blue is representing the days that had rain. So such a problem would have to utilize supervised learning. We also have what we call models, and a model is just a representation of some sort of phenomenon. Basically, two types of models mathematically, and those are deterministic models, those that have no randomness, and those that are considering randomness, and for those we call them the probabilistic models. For deterministic models, these hypothesize exact relationships and used when prediction errors are normally negligible. We also have probabilistic models, and these hypothesize mainly two components, deterministic and random error components. We have types of probabilistic models, and these include regression models, correlation models, and other models that can be included to that list. Let's talk about regression models first. So regression models are just representing relationships between one sort of dependent variable and another that is independent, and we shall call that the explanatory variable. We have a couple of steps followed for regression models, and the first is always to hypothesize a deterministic component or the deterministic components, and then to specify the probability distribution of the random error. After that, we evaluate the fitted model that we have made, and after that, we use it to predict a new set of data that we're trying to use the model with. And under regression, we have what we call linear regressions, and these are just relationships where the variables sort of create a linear function. I also have a line of best fit, and this is normally gotten using the least squares. The best fit is just the difference between the y values and the predicted values being the minimum. So we're trying to find a balance between the predictions and the actual values. Just in the middle there, that's where we normally use put a line of best fit. So just to illustrate this, we can see a diagram here showing us regression. And as you can see, the data points are separated using the line of best fit. And we see the data of a class of, non-rainy days. And the rainy days just at the bottom using the blue dots. The line of best fit just separating the two classes. But this is more of a hypothetical situation. Normally, real data in the real world will look much more like this, having a bunch of outliers. As you can see on the side that has the red dots, we have a couple of blue dots in the data. And on the side of blue dots, we also have a couple of red dots in the data. So this is what a normal data set will normally look like, having a couple of outliers. And the line of best fit just finds that balance between the two classes, basically, for regression models. And this is just to illustrate what a linear regression would look like. We see that the data points are sort of forming a line. And this would produce a linear function if a line of best fit is applied, just as we can see over there. So normally to classify this data, we'll use a couple of algorithms, and one of the ones that we use is the k-nearest neighbors algorithm, which is a KNN. And we can have two sorts of models, and normally we have a parametric model and non-parametric model. And for a parametric model, we know which model exactly to fit the data. And then for a non-parametric model, we shall have the data telling us what the regression will look like, just like the graph that we looked at previously. And in the KNN algorithm, we normally have data sets that we can use with this algorithm. One of them is the iris dataset, and this sort of dataset works with iris flower dataset. And these have attributes like the sepal length, in centimeters, sepal width, we have a petal length and a petal width. Those are the attributes of the iris dataset. So just to talk about the KNN algorithm just a little bit, we shall consider a new point on this graph. And this is the point that looks a little bit white on the screen. The others are red and blue, but there's a very white one slightly um, slightly over here. So as we look at this white point, for the KNN algorithm, we shall consider a certain number of neighbors. And when we look at all these neighbors, we shall be able to determine what class the new point falls into. So as we can see for the white point, it is surrounded by one red point, and then the others are mostly blue. So this, if all these points were to vote, normally we allow the points to vote, each point having a vote, and the class with the highest votes will normally win. So for this case, if there are more blues, we shall have that point also turning into a blue point for the KNN algorithm. So we have a couple of steps for the KNN algorithm, and those are calculating the distance between the training data and the test point, finding the nearest K neighbors by sorting those pairwise distances, and classifying the point based on a majority vote, as I explained earlier. So then we also have a couple of notes here, and that is we should never tune hyperparameters using the test data, because the ultimate goal of any machine learning algorithm is always to perform well on unseen data. Changing the hyperparameters on the algorithm based on how well it performed when the test data contradicts this idea. In other words, it will cause a sort of overfitting problem. And we have a couple of distances that we normally use with this algorithm. We have the Euclidean distance and the Manhattan distance, and the difference is that the Euclidean distance is used if the dimensions are being measured as or similar properties, whereas for the Manhattan distance, the dimensions are normally dissimilar. So if you remember in AI, when we were talking about heuristic functions, we use the Manhattan distance as normally just the difference in, let's say, the y coordinates and the x coordinates. So it's normally used on grids, whereas the Euclidean distance is just like a straight line distance between 2 points. And we have normally features being normalized for such algorithms, and this is just to create a common scale for features that are important but will be needed to be handled together. So to create a common scale for those features, we shall have to normalize them. We also have KNN applications here listed, and we normally use it in text mining. This is just to normally group documents with similar text, agriculture, where we can be able to find out diseases by grouping characteristics of let's say like pest effects and diseases of plants. That's an application we can have in agriculture. We also have in finance, and can be used for things like stock markets. We also have Kaggle competitions, and these are just applications in data science. I have a couple of pros for KNN, and it's easy to explain, it's simple to understand, extremely powerful, doesn't require any assumptions or data distribution. It's the first choice when there is no prior knowledge or very little knowledge to problems. It can also be used for both regression and classification problems. It can be used easily with multi-class datasets. We have a couple of cons, and these are the efficiency of our algorithm declines very fast as the dataset grows, comes to a cost of making the prediction step relatively expensive, comes at a cost, sorry, every time a prediction is to be made, such as for the nearest neighbor in the complete training set. So this is a problem because it has to measure every single point to find out the distance. And there are ways to get about this by using data structures that can avoid that or lessen that amount at time. That's why it's a problem. It suffers from skewed class distributions, meaning if a specific class is frequently occurring in a training set, then it's most likely to dominate the majority voting of the new examples. We talked about voting of the nearest neighbors, and can't work if there are any missing values. Also talk about overfitting just a little bit. So we have a data set here where we have the red dots and the blue dots. So as you can see, there's an outlier in the blue section of red. So normally if I were to draw the line of best fit, it would look something like that. But overfitting comes in when we try to accommodate the outlier for a test data set, and it would look something like that. So this sort of model whereas it will predict accurately for this test data set, if it is made to work on an unseen data set, it will fail, because a point that could be blue but falling in that extra section of the red zone that is on the blue side, it will end up being classified as red, yet it should have been blue. So this model would fail. We'll go on to talk about decision trees. And decision trees are normally applied in reinforcement learning. We have them in Markov's decision processes, and then we have trees being applied. So normally a tree has a root node, and this root node will break out into children using a specific branching factor. Here we have a tree that is branching out into with a branch factor of 3, the children having a branch factor of 1 each. So under decision trees, we have what we call a Gini impurity. This just measures the frequency at which any element of the data set will be mislabeled when randomly labeled. The Gini impurity is calculated in a specific formula, which we will not talk about right now, but we'll talk about a couple of things that are used with that. That's the Gini index, which has values in the interval of 0 to 0.5. Then let's have what we call the entropy, which just has an interval 0 to 1. Now, the entropy is a little bit difficult to calculate because it involves the use of logarithms, and so people normally will, prefer to use the Gini index for calculations. Now, when handling trees, we have ways in which we reduce the time for searching through the whole tree. And that's normally through pre-pruning. This is done by specifying a maximum depth for the implementation. And while we are doing this, it turns out that it's actually not a very good thing to do. As the approach, sometimes after, because after like a perfect split, you may have had a seemingly worthless split earlier on in the tree, and this can tend to be a problem. So to reduce on this problem, we use the algorithm with other algorithms like post-pruning to, improve its performance. Talk about information gain, and information gain is basically just a difference in entropies. This is normally biased for the attribute with many outcomes for this case. So the attribute with a larger number of distinct values will be preferred. We have a couple of pros for decision trees, and these are easy to interpret. It's easy to visualize, has no assumptions about distributions because of the non-parametric nature of the algorithm. It can easily capture nonlinear patterns, requires fewer data processing from the user, no need to normalize columns. And it can also be used for feature engineering, such as predicting missing values. That's no problem whether the inputs and outputs are binary, categorical, or continuous. We have a couple of cons, and it's sensitive to noisy data and can overfit this noisy data. Small variation in data can result in different decision trees, just by bugging and boosting algorithms, reduced with imbalanced datasets. So it's biased with imbalanced datasets, and therefore it is recommended to balance out the dataset before creating the decision tree. So the algorithms not yield global optimum tree structures. As the branching goes deeper, you get exponentially less data. Talk about ensemble learning and random forests. Ensemble learning is just combining mediocre models into one supermodel. And for this, we normally use what we call a bootstrap, and this addresses a challenge in statistics, which is just having a population sample and using it to to get information about an entire population. You just have a small number of people, but you want to get information about a whole lot of people. So while handling this problem in ensemble learning, we tend to use bugging, and bugging is just getting different models, different bootstrap training sets, and then using their predictions, averaging them to get one prediction for that supermodel that you're using. This basically improves accuracy, but it's always expensive on interpretability. So we have something we call a random forest algorithm, and it's a type of bugging algorithm. It's a collection of decorrelated decision trees. They are built as follows. As you can see, for every tree, we subsample the value examples with replacement bootstrapping, and for each subsample, we choose attributes at random, randomly pick features in each split, and we build the tree only on these random features with the current subsample. Talk about also some pros for this algorithm. It's robust outliers, works well with nonlinear data, while it lowers the risk of overfitting and runs efficiently on a large data set. It also has some cons, and it's biased while dealing with categorical variables, as slow training, not suitable for linear methods with a lot of sparse features. But the algorithms also do not yield a global optimum tree structure here. We have two definitions that are normally tricky here, and we can find out their difference. We have the difference between bugging and boosting. So boosting is just sequential tree growing, but with weighted samples. And for bugging, we have parallel tree growing with subsamples. We'll talk about support vector machines. So support vector machines normally prefer correct classification over agent maximization. They can detect outliers and also ignore them. So we'll look at a sample data set here. We have two sets of data classified, and we could either separate this data using a line of, let's say, best fit that is just vertical. The problem with this line is that data that may be belonging to the blue side and it's on the lower side of the red division would be misclassified as red. It would identify more with the blue. So this would not be a very good division or a line of best fit. Then we have a line of best fit that would be so close to the red. And the problem with this one is that data that may be very close to the red, but on the side of the boundary that is allocated to the blue would also be misclassified as blue. And so this would also not be very effective. So the best line of best fit would be the one that is approximately in the middle. And that's what SVMs are for, finding the best classification possible. So the good thing about SVMs is that they can actually go beyond 2 dimensions. So we have a data set like this where we cannot exactly draw a line of best fit. So we shall have to draw something like a circle to divide the data. So talk about clustering, and clustering is normally used in unsupervised learning. And here we normally have a form of a function that is just finding means that will be used to divide the data into clusters. So unsupervised learning is basically used for data that is not labeled, data that is without features. And yeah, it's so whenever the data doesn't have sort of features that are descriptive of the data, and we don't have any other information about the data other than the data itself, we'll use unsupervised learning to sort of create groups from the data and infer similarities and things like that. So kind of function is find that means that will help in grouping this data. We have things like gamma values, and they have effects depending on whether they're low or they're high. Just looking at k-means clustering, we have a data set here that is, unsupervised. We shall have our means. The means are the data means, the blue, the red. So those means will then group the data into groups, basically, depending on what is closest to that mean. And we see that 3 groups are created since we have 3 means here, and that's why it's called a k-means. The k being the number of groups required, and that will also be the number of means that the data is being, divided with. We have some pros. It's simple, easy to understand. It's considered a linear algorithm. It's the most popular clustering algorithm. Have some cons, only applicable if the mean is defined. It's sensitive to outliers, sensitive to initial seeds. It's not suitable for discovering clusters that are not hyperellipsoids or hyperspheres. So lastly, we'll have to talk about the principal component analysis, which is just the PCA. And the goal of this is to reduce the dimensionality of the data while keeping information loss to a minimum. It assumes variables are linearly correlated, and if the correlation is not linear, the PCA will not be efficient. So it performs this by lossy compression, and this just means information being is lost. That is when it's insignificant. When insignificant components of it are like taken off, and this is done. Scaling of variables should be documented and should not be adjusted to match prior knowledge of data. Since each PCA is a linear combination of the original features, visualizations are not easy to interpret or to relate to original features. So we're having data with very many dimensions, can have features that are over 2, but it's all being compressed into the least amount of features can be represented in. So you have probably, let's say, data that has about 4 dimensions being represented in a 2-dimensional way. And that's the benefit of PCAs, trying to squeeze as much information into as little information as possible, taking out what is relevant and keeping what is relevant. So applications of this are normally image compression, pre-processing steps for classification, regression, and clustering tasks. Also in facial recognition, this is for eigenfaces where the elements of a face that are crucial are kept, but the ones that are insignificant are normally not kept. And then we also have what we call data visualization. So yes, that has been it from me. And thank you so much for listening.